So here's the nitrogen cycle pre-industrially. So think about the year 1600. All the units are going to be teragrams, or 10 to the 12 grams per year today. As I said, that's a large unit to think about, but at least it'll be consistent through the day. We're going to confine ourselves really to the left-hand side of this diagram, which is the terrestrial side. There's a lot going on in the ocean here. I have never done an analysis of anything with a salinity approaching seawater, so I have no general expertise in that arena. But I'm going to dump a lot of nitrogen into the ocean and let the people here take care of it, and understand what happens to it once it gets there. So we'll be working over here on the left side. And pre-industrially, there were really a couple of sources of nitrogen that fed the plant growth and soils on the terrestrial side of the cycle. The first being biological nitrogen fixation. That's by largely by plants and the leguminosae that harbor nitrogen-fixing bacteria in association with their roots, and asymbiotic nitrogen-fixing bacteria in soils. And they added about 120 teragrams of nitrogen to the land surface. And that was about 10% of the plant demand pre-industrially. So you get the idea that the amount of nitrogen circulating pre-industrially was fed by biological nitrogen fixation, but it spent several years there, being taken up by plants, accumulated in leaves and branches and roots, and then dumped back to the surface and decomposed and released for uptake again. So once an atom of nitrogen fixed by biology got entered into that terrestrial cycle and spent a couple of years circulating, but then eventually got away. And why do we know that's true? Well, ever since the beginning of environmental chemistry and agriculture, humans have recognized that the land surface is almost everywhere starved and deficient in nitrogen. It's the basis of nitrogen fertilizer for agriculture. And so this continual input of nitrogen to the land surface just makes sense that it must have been balanced by equal losses of nitrogen to maintain this kind of state of starvation of soils for available nitrogen. So you can hypothesize, don't even have to hypothesize, that rivers carried a fair amount of nitrogen to the sea, and that denitrifying bacteria, which we'll spend a little bit of time on today, converted a lot of that nitrogen from the land surface back to the atmosphere to cycle again. And we can, of course, this becomes it's almost too tidy to have 125 coming in between lightning and biological nitrogen fixation and 127 going out. And that's the other nice thing about these cartoons, is you can force things to come close to balance because nobody was there to check it in 1600. But the river flow number, for instance, is estimated from pristine rivers today, and then extrapolated to what rivers like the Mississippi and the like must have carried pre-industrial. Okay, so what did we do? Along about early 1900s, Haber and Bosch, a couple of German industrial chemists, developed the Haber-Bosch reaction process, motivated by the fact that Germany was cut off of Chilean and other deposits of nitrate to make gunpowder and explosives with, so they were looking for an alternative way to make explosives, and perfected the ability to take nitrogen, which fills 78% of the atmosphere in this room. It's a triple bonded molecule, very inert, colorless, odorless, almost unreactive, to convert that into industrial nitrogen, ammonia and nitrate that could be used for explosives. And after World War I, and particularly after World War II, this became the basis of industrial fertilizer. A few summers ago, I went out into our own garage closet and grabbed a bag of fertilizer, Growers Special, whatever that means. And like all fertilizers, it'll have 3 numbers on it, and the first number is the percent nitrogen in that bag, and you can see the breakdown here of ammonium nitrate and urea and other forms that are in there. Number 2, second number 2, I guess, That's phosphorus. Third number is potassium. Those are the big components of fertilizer. And almost always, unless you're trying to do something very special to your garden, the nitrogen number will be the largest, and that fertilizer, unless you've gone organic, will have been produced in a petrochemical plant somewhere around the world. A lot of it's produced in Louisiana in this country and shipped worldwide and across the U.S. It is used in vast quantities, much vaster than you want to put on your own rose garden or whatever. Throughout the Midwestern U.S., corn in particular is fertilized something on the order of 200 kilograms per hectare in many cases. And actually that has its own climate change interaction because a lot of fossil fuel goes into producing nitrogen fertilizer, which of course if that is growing a corn crop to produce biofuels to replace gasoline, you can see, well, gee, is this a good balance? We use a lot of fossil fuels to produce the fertilizer, and then we say we're doing a good thing because we're getting biofuels out of it. This is the kind of intersection of biogeochemistry and economics that I think is great fun in today's world. But a lot of it's spread around the world very actively. Malakoff, Schimmel, and others. This is Vinay and Ija's graph from down in North Carolina State, in which he's got both human population in the green there from the year 1900 up to the year 2000. This is the use of nitrogen fertilizer. You can see that kicks in with great gusto and enthusiasm after World War II. And he makes, I think, a pretty effective argument that we wouldn't be on the population growth that we are now if it wasn't for the Haber-Bosch reaction and the widespread availability of inexpensive nitrogen fertilizer to feed what's now, today is 6.8 billion people or something globally. He has a book which, this book, this is a great book if you want to know about the Haber-Bosch reaction. I will say it's probably more than you want to know about the Haber-Bosch reaction. But if you want to know about it, this is the place to go. And it is also, I think, pretty well written and an interesting read in that fashion. But we'll come back to the biogeochemistry of this. So this is today, the modern nitrogen cycle. Again, the units are teragrams, same units as before. The human-derived inputs are roughly 150 teragrams arriving on the land surface. That's a combination of the Haber-Bosch reaction for nitrogen fertilizer, as well as a certain amount of air pollution from coal-fired power plants and high compression automobile engines. But of course, the important thing is that we've essentially doubled the nitrogen input from biological fixation, which itself has gone up a little bit from 120 to 140 teragrams as a result of the widespread planting of soybeans and other nitrogen-fixing crops. So overall, we've vastly increased the amount of nitrogen on the land surface. And my question for today is we're going to chase those nitrogen atoms. Where has that nitrogen gone? How much has gone in different pathways? Does that give you some idea of which pathways are likely to be ones in which human impacts are showing up? Do we have pathways that might actually give some opportunity to policymakers for cleanup? And I think there'll be a little bit of something for everybody there. So that's our question is, where did all this nitrogen go for today? And I'm going to move through five pathways of it. We're going to move through some of them faster than others because some of the estimates of where the nitrogen was going or is going had been done fairly recently in the literature, and whenever I run into something like that, my first reaction is, boy, unless I see a way to do it better, there's no point doing it over. And therefore, we want to be able to save some time to work on the things that are truly unknown and maybe haven't been estimated before.